Okay, so we're in section 8.2 now, and we are looking at solving homogeneous linear systems. So in the previous section, we talked about what a linear system of differential equations looks like and how to represent it in matrix form, how to verify if a solution or if a given if a given vector is a solution to that system. We haven't talked about how to come up with a solution ourselves given a system of equations, and that's what our goal is now. So again, we're focusing specifically on homogeneous linear systems right now. And this is another section where it's really going to help you if you've had linear algebra, because we're going to be talking about a couple of things that are linear algebra topics. Right in the beginning here, we're going to talk about eigenvalues and eigenvectors. That's a major topic in linear algebra. We do not have the time in this class to give a full development of that concept. We're just going to talk about enough of it to be able to do what we need to do in this chapter. So if you've had linear algebra, you should have much stronger familiarity with this. If you want more background on eigenvalues and eigenvectors, you can jump over to my linear algebra playlist on my YouTube channel, and the chapter 5 material in there deals with that. It's also going to really help you if you know how to solve systems of equations, systems of linear algebraic equations. And again, that's a big thing that you talk about in linear algebra, but you also talk about that in elementary and intermediate algebra. There's various different ways to solve systems of equations. If you know how to use Gauss-Jordan elimination, which you may have learned in a pre-calculus class, and if not, that's definitely something that's covered in linear algebra. That's one way to solve systems of equations, and it's pretty typical of how you would do it in a section like this. But that's just my little disclaimer. Again, linear algebra is not a prerequisite for this course, so if you haven't had it, you can technically get by in this section. It's just going to take probably a little bit more time for you to wrap your head around the concepts that we're talking about. Anyways, that's enough time spent on the disclaimer. Let's go ahead and get into it. So if you remember from the last section, we said that the matrix form of a homogeneous linear system would look like this. X prime equals AX, where A is that coefficient matrix. And we're assuming that the coefficient matrix has constant entries here. Now, if that's the case, then every solution, and again, I'm making a statement here without proving it, but if you go back to the previous section when we looked at some solutions to linear systems, if you got through the homework in that section, you should see that this was generally the case. We're going to take it on faith here that every solution is going to have this form. So again, that X there is the solution vector to this system. And it's always going to have the form of some column vector of constants. The K's here are constants times an exponential function. And this shouldn't be super surprising, because if you go back to chapter 4, section 4.3 specifically, where we talk about solutions to homogeneous linear equations, not systems of equations, but just equations with constant coefficients, all of our solutions had this form as well, without the matrix here. In fact, what we had were linear combinations of exponential functions. And what we did is we broke that down into 3 cases, because remember, we came up with the idea of an auxiliary equation back then. The solutions to that auxiliary equation would determine what shows up in the exponent here. And then there's 3 possible cases that we had to look at in the case of the auxiliary equation solutions. There were, what would happen if you had real distinct roots, what would happen if you had repeated real roots, and what would happen if you had complex roots for that auxiliary equation. In all of those cases, you have an exponential function, but in the complex case, we manipulate that exponential function using Euler's formula and get a different expression involving sine and cosine. So this is kind of an extension of that exact same thing. That's for the same reason we're getting that exponential function showing up here, except instead of a single function, we have a system of, or a set of functions that act as a solution to the system, which is what this column vector is there for. Okay. Here, I'm going to call that column vector K, just to make it easier to work with in what follows here. Now, notice if I were to look at the derivative of this to verify, or to plug something in for x prime here, the derivative of this, if I were to distribute that e to the lambda t into each one of these, I would just be taking the derivative of each entry separately, but we also saw in the previous section, since these are all constants, I can also just take the derivative of this guy on its own and leave the constant vector alone. That lambda would pop out after taking that derivative, right? And this looks so similar to this that if I'm going to use this notation, this is the same thing as k lambda e to the lambda t. So that's what x prime looks like if x looks like this. Okay, now if I plug both of these into my original system up here, then on the left-hand side I'll get this expression, that's where x prime showed up. On the right-hand side I should have ax, a times this, or ak e to the lambda t. Now, again, these are matrices. These are technically column matrices on each side of this thing. And again, this is not a linear algebra class, but in a linear algebra class, you talk about the valid arithmetic that you could do with matrices. And one thing you can do is if you multiply by a scalar, you can divide by that scalar as well. What we have here is e to the lambda t showing up on both sides, which is always non-zero because it's an exponential function. And we're allowed to divide both sides by that. So that simplifies this a little bit. I have lambda k. Notice I just brought the lambda to the front just for notational purposes, and then ak on the right. Okay? Or alternatively, if I subtract the lambda k from both sides, I could also write that as ak minus lambda k equals 0. Okay, now here's something you may not be familiar with if you haven't had linear algebra, but we're going to introduce the identity matrix here. And if you don't know what an identity matrix is, that's okay. I'm going to give you just enough information to know what we're using it for. So I'm calling it the n by n identity matrix. It has to be n by n to be compatible with multiplication with this matrix K, which remember had n entries. The identity matrix is basically, it does what the number 1 does in the real numbers when you multiply. So 1 times any real number is that original real number. It doesn't change that real number. The identity matrix is the same thing as long as it's the correct size so that multiplication is compatible. So in other words, the identity matrix I times k is still just going to equal k. Multiplying by the identity doesn't change it, okay? I'm not going to go into detail on what the identity matrix looks like if you write it out explicitly because we don't really need that much information here. Actually, I probably should. So let me write that. I just realized we kind of do need that. So the identity matrix I is going to look like this. 1, 0, 0, 0, 0, 0. We get all zeros except for that first entry there. And then 0, 1. These will all be zeros here. And then 0, 0, dot, 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 1. So basically what this is the... we should have other entries here too. It's any n by n matrix that has 1s along its main diagonal, going from top left to bottom right, and zeros everywhere else. So this is the identity matrix, and we could show that if you multiply it by any matrix that's compatible with the dimensions of this thing, then you get that matrix back again. The reason we're introducing this identity matrix is because we're going to use the distributive property to factor something out of this expression. Notice I have a k showing up here. You can't just factor the k out as is, because what would be left is a minus lambda. Remember, a is an n by n matrix, and lambda is a scalar. It's a real number. You can't subtract a real number from a matrix. They're two different objects, right? So simply factoring that k out without thinking about what you're doing gives you something invalid. However, if I were to replace that k with ik because they're equal, then I could factor the k out because I is an n by n matrix. And so lambda I is what would be left here. And I have an n by n matrix minus an n by n matrix. That's valid. I can do that. Okay. Now the purpose behind doing this is to obtain this equation here. Notice the bold 0 that's showing up here. That means that that's the 0 matrix. Okay. It's a matrix containing only 0 entries. It's not the number 0. In linear algebra, we would look at this as a system of linear equations because again, it's an n by n matrix multiplied to an n by 1 column matrix. So this is like the coefficient matrix. This is like the column matrix that contains our unknowns, and it's set equal to some other column matrix. That's the form of a linear system. If I were to write this out explicitly, the linear system would take this form. Now, the A11, the A12, all that stuff, those A's come from the matrix A. And lambda, if you think about it, if I multiply lambda to this identity matrix, which is what's happening here, then this matrix is just going to look like this. Lambda, lambda, along all the main diagonal entries, and zeros everywhere else. Okay, dot, 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 dot. So that's what lambda I would look like, because you're just multiplying all of these entries by lambda, right? And if you subtract that from all of the entries of A, then you get this linear system, where all of the non-main diagonal entries of this matrix would look the same as just the entries of A, because you're subtracting 0 from those. All the others, you're subtracting lambda from those. So along the main diagonal, we have these coefficients that look like A11 minus lambda, A22 minus lambda, dot, 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 ANN minus lambda. And we're multiplying that to the column matrix K, which would give me K1, K2, and so on. Remember the K1, K2 through Kn, those are like the unknowns that we're solving for in this system, okay? Now in linear algebra, we can show that when you have a homogeneous linear system like this, obviously this will always have the trivial solution. If I plug a 0 in for all of my k's, all of these will always come out to zeros. So the trivial solution is definitely a solution to this. But if it's going to have non-trivial solutions, that can only occur if the determinant of your coefficient matrix is equal to 0. And again, that's something that we prove in linear algebra. We're just taking it for granted here. So that leads to this result. The determinant of A minus lambda I equals 0. And this determinant, if you evaluate it, is going to produce a polynomial. It always produces a polynomial, which we'll see in the examples that we do. The equation that you're getting here, that polynomial equals 0, is what we call the characteristic equation of the matrix A. And the solutions to this thing, where the unknowns are these lambdas here, the solutions are what we call eigenvalues of A. And then, if you remember where we're using this matrix, it's showing up in this system up here. You have this K here, which represents the unknowns that's being multiplied to that coefficient matrix. Any non-zero K that corresponds to a given value of lambda, a given eigenvalue, is called an eigenvector of A corresponding to lambda. Okay? Now, that, again, if you have not had linear algebra, I'm sort of expecting that the last 10 minutes was kind of like, what? You know? Because, again, sort of the nature of this course, we're expected to use a lot of linear algebra without requiring you to have it as a prerequisite. I have my own personal opinions about that. I don't really think we should be teaching this class without linear algebra as a prerequisite, but I don't get to make that decision. So unfortunately, again, topics like this, eigenvalues, eigenvectors, which you would normally spend a lot of time developing in a linear algebra class, we kind of have to rush it in this class. So if none of that development made sense, you'll be able to get by. You just need to know how to solve these, come up with these characteristic equations and solve them. You don't need to go through all that derivation that we just did. So what I'm going to do is talk about a theorem. Actually, sorry, let's back it up a step. Remember, what we're aiming to do here is solve these characteristic equations, which are they're polynomial equations. So we're solving polynomials equations. From what we know in algebra, and from what we discussed back in section 4.1, this naturally leads to 3 different cases. The solutions can be real and distinct. they can be repeated real roots, or we can have complex roots. So that leads to the three cases that we consider here. When we're finding eigenvalues for a matrix, which we need in our solutions for these linear systems, we can have distinct real eigenvalues, we can have repeated real eigenvalues, or we can have complex eigenvalues. And just like in section 4.1, we need to treat this in three separate cases. So we have a lot of examples to look at. Now, the guiding theorem that we're going to use in the case where we have real and distinct eigenvalues for a homogeneous system is this one. So let's suppose that we have a matrix A that's showing up in a system of linear differential equations. We solve the characteristic equation for that matrix and get a total of n distinct real eigenvalues, okay? And then let's suppose we find corresponding eigenvectors for each of these eigenvalues. Now, one thing I'm going to say, and I'll mention this again in the example, is that for any given eigenvalue, there tends to be an infinite number of eigenvectors associated with it, okay? We just need to find one eigenvector that corresponds to each one of these, and we'll talk about how to do that in the example. Then if these are corresponding eigenvectors, then the general solution, it says of 2, but that's of that kind of general system that we saw on the previous page. On the interval negative infinity to infinity is given by this. Notice what it is. It's a linear combination of the K1, K2, K3, and so on and so forth, these eigenvectors, times an exponential function of the form e to the lambda 1t, e to the lambda 2t. The lambdas up here are the eigenvalues corresponding to the eigenvectors showing up in the same term. Okay, so again, since we haven't done any examples, this is probably all sounds like gibberish. So we're going to go launch into an example now. Okay, we want to find the general solution to this system. dx dt equals 2x plus 3y, dy dt equals 2x plus y. Now, this is not in matrix form, but if I were to write it in matrix form, the matrix A, in fact, well, let's actually write it this way. In matrix form, this would look like x prime equals 2, 3, 2, 1 times x. Remember, x is the matrix, the column matrix xy. This guy is A. Okay, so that's my coefficient matrix. Now, in order to proceed with what we just talked about, I need to come up with that characteristic equation. So the characteristic equation is this: the determinant of A minus lambda I equals 0. Okay? But what is that determinant? Well, remember, the determinant, the matrix A minus lambda I is going to look exactly like the matrix A. The only difference is that I'm subtracting lambda from the main diagonal entries. So that's going to look like this: 2 minus lambda. This 2 and this 3 are not going to change. 1 minus lambda. Now, before I go any further, I'm going to mention something. If you do go and look at my linear algebra videos, in my linear algebra videos, if I'm remembering correctly, we do this determinant the other way around. We do lambda I minus A instead of A minus lambda I. In those cases, I would have lambda minus 2 and lambda minus 1 here, but I would also have I would have the opposite of all the other entries in the matrix. Depending on whatever textbook you look at, you'll see it one way or the other. They both do the same thing. They both get you correct eigenvalues. And there's a reason why one might be preferred over the other. In this book, though, we're going to do A minus lambda I. So if I evaluate this determinant, that's equal to 2 minus lambda times 1 minus lambda minus 3 times 2, which is 6. This is equal to lambda squared minus 2 lambda minus 1 lambda, so that's minus 3 lambda plus 2 minus 6, which equals lambda squared minus 3 lambda minus 4 which equals lambda plus 1 times lambda minus 4. Okay? And we need that to equal 0. Again, that's what the characteristic equation has here. So now, this would tell me that the eigenvalues for this matrix A are -1 and 4. Those eigenvalues are needed because they show up in our general solution. But I also need to find eigenvectors corresponding to each one of those. And how do we do that? Well, remember, what an eigenvector is, if I come back here, an eigenvector is what I would get by taking either one of those eigenvalues and plugging them in for this lambda here, and then multiplying it by this column matrix of unknowns and finding a vector that would work as a solution here. So I need to start by looking at A minus lambda I. Okay, let's focus first on the eigenvector lambda. I'm going to call it lambda 1 equals -1. That was one of the solutions to this equation right here. So I would want to take that -1 and plug it in to the lambda here, right? So I do A minus lambda. So what does A minus lambda look like? A minus lambda I, sorry. A minus lambda I is going to look like this matrix. Okay? 2 minus -1, so that's 3. Remember the 3 here and the 2 here aren't changing. 1 minus -1, that would be 2. Okay? So that means the system of equations that I'm looking at. Remember, I'm multiplying this by the column vector k1, k2. That's this guy. Which, after doing that multiplication, would look like 3k1 plus 3k2 on top. And we want that to equal... equal 0, because this is a homogeneous linear system. 2k1 plus 2k2 equals 0. Now, this is something that generally will happen with finding eigenvectors. These two equations are equivalent to each other. What basically happens is if you try to solve this using elimination, one of these equations is going to reduce down to 0 equals 0. It's going to disappear. And what that implies is that you have an infinite number of solutions to this that we can parameterize. So if I were to solve, for example, this first equation, this would imply that k1 is equal to -k2. Okay? K1 is equal to -k2. And that's so basically the set of all ordered pairs where my first coordinate or my first component is the opposite of my second coordinate. All of those would work as solutions to this, an infinite number of solutions. Okay? Now, so that means there's an infinite number of eigenvectors I could choose to correspond to this eigenvalue -1. All I would need to do is assign any number I wanted to k1 and then find the corresponding value for k2, put them into a matrix, and then I would have an eigenvector. So for example, I could plug 9 in for k1, giving me k2 equals -9, right? Technically, I could think of plugging something in for k2 and taking the opposite of it, but it kind of works both ways. So generally, when we're picking eigenvectors, we want to pick kind of the simplest one. We want to pick the simplest non-zero vector that would work under this condition. And for our purposes, I think 1, -1 is the simplest. So what I'm going to do, this is a capital K1, corresponding to the capital K's showing up here. Capital K1, if I assign a 1 to K1, then K2 would have to equal -1. So that's going to be the eigenvector that I use for this eigenvalue. Next up, we want to look at an eigenvalue of 4. That was the other solution to our characteristic equation up here. In this case, A minus lambda I would look like, so remember, I'm subtracting 4 from the main diagonal entries of A. 2 minus 4 is -2. I'm still going to have a 3 and a 2 here. 1 minus 4 is -3. This corresponds to the system of equations, negative 2k1 plus 3k2 equals 0, and 2k1 minus 3k2 equals 0. Again, if you try to solve this system using elimination or Gauss-Jordan or anything like that, one of these equations is going to drop out completely, which means you, once again, will have an infinite number of solutions. So if you just solve one or the other, you're going to see here that we end up with k1 equals 3/2 k2. Okay, and once again, we can assign any value to the k1 and k2 so long as this equation is equal or it is true to get an eigenvector. So for example, I could plug a 1 in for k2, for example, which would mean k1 is going to equal 3/2. So I could use the matrix 3/2 1 as a eigenvector. But kind of standard practice with eigenvectors is we try to avoid fractions as much as possible, just to make the work that we do with them a little simpler. So I'm actually going to set k2 equal to 2 so that it cancels out this denominator when I plug it in, giving me k1 equals 3. And that's going to give me k2 equals the matrix 3, 2. Okay? So that is going to lead to the general solution. Again, we're using this theorem, which requires us to know all of the eigenvalues and an eigenvector associated with each one. The general solution is going to look like this. C1 times the eigenvector that I found here, k1, which looks like 1, negative 1, times the exponential e to the power of that eigenvalue times t. So negative 1t or just negative t. Plus C2 times K2, this eigenvector, times the exponential, which has its eigenvalue that was corresponding to this, 4t. And that would be the general solution for that linear system. Okay? We have a lot more to do, but that's all the time I have for this video.